In computer engineering, a logic family may refer to one of two related concepts. A logic family of monolithic digital integrated circuit devices is a group of electronic logic gates constructed using one of several different designs, usually with compatible logic levels and power supply characteristics within a family. Many logic families were produced as individual components, each containing one or a few related basic logical functions, which could be used as building blocks to create systems or as so-called glue to interconnect more complex integrated circuits. A logic family may also refer to a set of techniques used to implement logic within VLSI integrated circuits such as central processors, memories, or other complex functions. Some such logic families use static techniques to minimize design complexity. Other such logic families, such as domino logic, use clock dynamic techniques to minimize size, power consumption, and delay. Before the widespread use of integrated circuits, various solid-state and vacuum tube logic systems were used, but these were never as standardized and interoperable as the integrated circuit devices. Technologies. The list of packaged building block logic families can be divided into categories, listed here in roughly chronological order of introduction, along with their usual abbreviations. Resistor transistor logic, direct coupled transistor logic, resistor capacitor transistor logic, diode transistor logic, complemented transistor diode logic, high threshold logic, emitter coupled logic, positive emitter coupled logic, low voltage positive emitter coupled logic, gunning transceiver logic, transistor logic, p-type metal oxide semiconductor logic, N-type metal oxide semiconductor logic, depletion load NMOS logic, high density NMOS, complementary metal oxide semiconductor logic, bipolar complementary metal oxide semiconductor logic, integrated injection logic. The families were derived from the logic circuits used in early computers, originally implemented using discrete components. One example is the Phillips-Norbitz family of logic building blocks. The PMOS and I2L logic families were used for relatively short periods, mostly in special-purpose custom large-scale integration circuits devices, and are generally considered obsolete. For example, early digital clocks or electronic calculators may have used one or more PMOS devices to provide most of the logic for the finished product. The F14C ADC, Intel 4004, Intel 4040, and Intel 8008 microprocessors and their support chips were PMOS. Of these families, only ECL, TTL, NMOS, CMOS, and BiCMOS are currently still in widespread use. ECL is used for very high-speed applications because of its price and power demands, while NMOS logic is mainly used in VLSI circuits applications such as CPUs and memory chips, which fall outside of the scope of this article. Present-day building block logic gate ICs are based on the ECL, TTL, CMOS, and BiCMOS families. RTL. The Atanasoff-Berry computer used resistor-coupled vacuum tube logic circuits similar to RTL. Several early transistorized computers used RTL, where it was implemented using discrete components. A family of simple resistor transistor logic integrated circuits was developed at Fairchild Semiconductor for the Apollo guidance computer in 1962. Texas Instruments soon introduced its own family of RTL. A variant with integrated capacitors, RCTL, had increased speed, but lower immunity to noise than RTL. This was made by Texas Instruments as their 51XX series. DTL. Diode logic was used with vacuum tubes in the earliest electronic computers in the 1940s, including ENIAC. Diode transistor logic was used in the IBM 608, which was the first all-transistorized computer. Early transistorized computers were implemented using discrete transistors, resistors, diodes and capacitors. The first diode transistor logic family of integrated circuits was introduced by Signetics in 1962. DTL was also made by Fairchild and Westinghouse. A family of diode logic and diode transistor logic integrated circuits was developed by Texas Instruments for the D37C Minuteman II guidance computer in 1962. But these devices were not available to the public. A variant of DTL called high-threshold logic incorporated Zener diodes to create a large offset between logic 1 and logic 0 voltage levels. These devices usually ran off a 15-volt power supply and were found in industrial control, where the high differential was intended to minimize the effect of noise. ECL. The ECL family, ECL is also known as current mode logic, was invented by IBM as current steering logic for use in the transistorized IBM 7030 stretch computer, where it was implemented using discrete components. The first ECL logic family to be available in integrated circuits was introduced by Motorola as MECL in 1962. TTL. The first transistor logic family of integrated circuits was introduced by Sylvania as Sylvania Universal High-Level Logic in 1963. Texas Instruments introduced 7400 series TTL family in 1964. Transistor logic uses bipolar transistors to form its integrated circuits. TTL has changed significantly over the years, with newer versions replacing the older types. Since the transistors of a standard TTL gate are saturated switches, minority carrier storage time in each junction limits the switching speed of the device. Variations on the basic TTL design are intended to reduce these effects and improve speed, power consumption, or both. The German physicist Walter H. Schottky formulated a theory predicting the Schottky effect, which led to the Schottky diode and later Schottky transistors. Schottky transistors have a much higher switching speed than conventional transistors because the Schottky junction does not promote charge storage, leading to faster switching gates. Gates built with Schottky transistors use more power than normal TTL and switch faster. With low-power Schottky, internal resistance values were increased to reduce power consumption and increase switching speed over the original version. The introduction of advanced low-power Schottky further increased speed and reduced power consumption. A faster logic family called fast was also introduced that was faster than normal Schottky TTL. IIL. The integrated injection logic uses bipolar transistors in a current steering arrangement to implement logic functions. It was used in some integrated circuits, but it is now considered obsolete. CMOS. CMOS logic gates use complementary arrangements of enhancement mode N-channel and P-channel field effect transistor. Since the initial devices used oxide-isolated metal gates, they were called CMOS. In contrast to TTL, CMOS uses almost no power in the static state. A CMOS gate draws no current other than leakage when in a steady 1 or 0 state. When the gate switches states, current is drawn from the power supply to charge the capacitance at the output of the gate. This means that the current draw of CMOS devices increases with switching rate. The first CMOS family of logic integrated circuits was introduced by RCA as a CD4000 COS, MOS, the 4000 series, in 1968. Initially CMOS logic was slower than LSTTL. However, because the logic thresholds of CMOS were proportional to the power supply voltage, CMOS devices were well adapted to battery-operated systems with simple power supplies. CMOS gates can also tolerate much wider voltage ranges than TTL gates because the logic thresholds are proportional to power supply voltage, and not the fixed levels required by bipolar circuits. The required silicon area for implementing such digital CMOS functions has rapidly shrunk. VLSI technology, incorporating millions of basic logic operations onto one chip, almost exclusively uses CMOS. The extremely small capacitance of the on-chip wiring caused an increase in performance by several orders of magnitude. On-chip clock rates as high as 4 GHz have become common, approximately 1,000 times faster than the technology by 1970. Lowering the power supply voltage. CMOS chips often work with a broader range of power supply voltages than other logic families. Early TTL ICs required a power supply voltage of 5 V, but early CMOS could use 3 to 15 V. Lowering the supply voltage reduces the charge stored on any capacitances and consequently reduces the energy required for a logic transition. Reduced energy implies less heat dissipation. The energy stored in a capacitance C and changing V volts is 1/2 CV2. By lowering the power supply from 5 V to 3.3 V, switching power was reduced by almost 60%. Many motherboards have a voltage regulator module to provide the even lower power supply voltages required by many CPUs. HC logic. Because of the incompatibility of the CD4000 series of chips with the previous TTL family, a new standard emerged which combined the best of the TTL family with the advantages of the CD4000 family. It was known as the 74HC family of devices and used the pinout of the 74LS family with an improved version of CMOS technology inside the chip. It could be used both with logic devices which used 3.3 V power supplies, and with devices that used 5 V power supplies and TTL logic levels. The CMOS TTL logic level problem interconnecting any two logic families often required special techniques such as additional pull-up resistors, or purpose-built interface circuits, since the logic families may use different voltage levels to represent 1 and 0 states, and may have other interface requirements only met within the logic family. TTL logic levels are different from those of CMOS. Generally, a TTL output does not rise high enough to be reliably recognized as a logic 1 by a CMOS input. This problem was solved by the invention of the 74HCT family of devices that uses CMOS technology but TTL input logic levels. These devices only work with a 5 V power supply. They form a replacement for TTL, although HCT is slower than original TTL. Other CMOS families. Other CMOS circuit families within integrated circuits include cascode voltage switch logic and pass transistor logic of various sorts. These are generally used on-chip, and are not delivered as building block medium-scale or small-scale integrated circuits by CMOS. One major improvement was to combine CMOS inputs and TTL drivers to form a new type of logic devices called BiCMOS logic, of which the LVT and ALVT logic families are the most important. The BiCMOS family has many members, including ARBD logic, ALB logic, ALVT logic, BCT logic and LVT logic. Improved versions with HC and HCT logic and LSTTL logic competing in the market, it became clear that further improvements were needed to create the ideal logic device that combined high speed with low power dissipation and compatibility with older logic families. A whole range of newer families has emerged that use CMOS technology. A short list of the most important family designators of these newer devices includes LV logic, LVT logic, ALVT logic. There are many others including AC, ACT logic, AHC, AHCT logic, ALVC logic, AUC logic, AVC logic, CBT logic, CBTLV logic, FCT logic and LVC logic. Monolithic integrated circuit logic families compared. The following logic families would either have been used to build up systems from functional blocks such as flip-flops, counters, and gates, or else would be used as glue logic to interconnect very large-scale integration devices such as memory and processors. Not shown are some early obscure logic families from the early 1960s, such as DCTL, which did not become widely available. Propagation delay is the time taken for a two-input NAND gate to produce a result after a change of state at its inputs. Toggle speed represents the fastest speed at which a JK flip-flop could operate. Power per gate is for an individual two-input NAND gate. Usually there would be more than one gate per IC package. Introduction year is when at least some of the devices of the family were available in volume for civilian uses. Some military applications predated civilian use. On-chip design styles. Several techniques and design styles are primarily used in designing large single-chip application-specific integrated circuits and CPUs, rather than generic logic families intended for use in multi-chip applications. These design styles can typically be divided into two main categories: static techniques and clock dynamic techniques. Static logic: pulse static CMOS. Differential cascode voltage switch. Cascode non-threshold logic. Pass gate, transmission gate logic. Pass transistor logic. Complementary pass gate logic. Push-pull logic. Output prediction logic. Cascode voltage switch logic. Dynamic logic. Four-phase logic. Domino logic. Footless domino. NORA, zipper logic. Multiple output domino. Compound domino. Dual rail domino. Self-resetting domino. Sample set differential logic. Limited switch dynamic logic.